Welcome to Caching in Python with LRU. My name is Christopher, and I will be your guide. This course is primarily about the LRU cache decorator in the functools library, but you'll need a bit of background to better understand what it is doing. In this course, you will learn about using caches to improve your code's speed, choosing from different caching styles, writing cached functions with the least recently used policy, and augmenting a decorator to add functionality. The code I'll be showing you was tested using Python 3.10. The LRU cache decorator has been around since Python 3.2, so if you're not running the latest, you're probably still okay. That being said, 3.10 has some great improvements on syntax errors, and it makes finding problems that much easier. You really should upgrade if you can. A cache is a common optimization in the computing field. It is used to gain speed in your programs at the cost of using up memory. Expensive calculations or data that takes a long time to fetch is put into the cache, and subsequent access to the same content can be returned more quickly. A lot of software follows what's called the principle of locality. That means if you've used it before, you're likely to use it again, or at least more likely than some other stuff. Python provides you a self-contained caching mechanism as a decorator. With a few small restrictions, you basically just need to wrap your function and you'll be taking advantage of a cache. In this course, I'll walk you through the trade-offs and show you both how to use this decorator as well as how it works. There are several different ways of writing a cache. In the next lesson, I'll show you some of the common implementations. In the previous lesson, I gave an overview of the course. In this lesson, I'll show you how caching works generally and a couple of different choices you can make in how you cache things. Software often exhibits the principle of locality. Recently used things are likely to be used again. This works at many different levels in your architecture. Memory blocks that were used before are more likely to be used again than other memory blocks. Stuff from the disk also often exhibits this behavior. If you have a complex calculation to do that is expensive to perform, there's a chance you may need that value again. And this is quite common on the web. Your browser has caches built in to avoid refetching things from the internet. Consider a news site. Even if it is updated regularly, the logos on it aren't likely to change frequently. Keeping the logos in a cache means saving the transit time of downloading them again. Caching values means you can get at them again quickly, but that comes at the cost of space. This cost is usually in memory, but it can also be at the cost of disk space. If the cost of computing something or fetching something is high, a cache will save you time if that value is ever reused. This is so common that your processor has this concept built in. Modern CPUs often have several layers of caches to reduce the number of trips to RAM. Virtual memory in your operating system allows you to have the total memory use of all your running programs exceed the amount of RAM you have. How the pages of memory are swapped in and out of RAM uses the same kind of mechanisms that I'll be showing you for your cache. And finally, you can take advantage of these concepts in your own code with the use of the right library. In Python, that'd be the functools library. To better understand caches, consider a chunk of data. I'm going to name this chunk of data 5. You'll see why in a second. The 5 block has some friends, 9 of them in fact. These blocks are big enough that only a few of them can be used at a time. Consider the base case of only being able to keep one of these blocks in memory at a time. When I need a block, I swap all of its contents into memory. And if I want something else, I have to wipe out what is there to make room for another block 6 in this case. There aren't a lot of choices to make if you can only fit one block into memory at a time, so let's increase our RAM. Now I've got 3 blocks. I'll load the 2, then the 7, then the 0 block. Now I have a decision to make. If I want to load another block, something is going to have to go. This decision in caching is called the caching policy. There are several different algorithms you can use to choose which of these blocks gets replaced. Let's look at several different kinds of caching policies. The first is called FIFO, short for first in, first out. This means that whatever got put into the cache first is the thing that gets removed when the cache is full. LIFO, or last in, first out, means the last thing that got put in the cache is the first to go. This mechanism favors whatever got loaded early on and then pretty much stays forever. LRU, or least recently used, determines which item in the cache was used the longest ago. This will be where the rest of this course concentrates. MRU, or most recently used, is LRU's cousin. And LFU, which just sounds rude, is least frequently used, where you keep frequency counters on the blocks and kick out the one that has been accessed the least. FIFO is pretty cheap to implement, but you might be getting rid of something that is used a lot. LFU optimizes for use, but takes a lot of extra bookkeeping. Every time you kick something out, you have to scan through to find the lowest frequency, or resort your list. Both of these can be expensive operations. LRU is a compromise between the two, hence why it is one of the more common policies. Let's see some of these in action to better understand the choices. Once again, I've got 3 spots for blocks. This time around, I'm going to skip the block part and just show you the numbers, but the idea is the same. Along comes a 3. The cache is empty, so the 3 gets inserted. Now a 5. There's still space, so 5 gets filed away. Now another 3. This is called a cache hit. Block 3 can be returned from the cache, and the cache itself looks the same before and after a hit. Remember, these numbers are really representing large chunks of data. You'd never just cache a single number. Now, the 9 block, it takes up the last spot. In the immortal words of Tim Curry, anticipation. So what do? Here's the 1 block, and the cache is full. This is called a miss. Now you have to decide what gets kicked out. With the FIFO policy, you look at the first thing that was inserted, which in this case was the 3. The 3 goes away and is replaced by the 1 block. Let's do that again. Here comes a 4, another miss. FIFO says the 5 should be replaced. And so it is. This cache can be implemented with an ordered list and a pointer. The pointer indicates what is to be replaced next, and when it is, the pointer advances by 1 spot. In the case of pointing to the last spot, the pointer wraps around to the first spot again. This is what I meant when I said FIFO is relatively cheap. You really only need 1 additional pointer to implement this method. Note that although the 3 was used, it was still the first thing to go, and that's the weakness of this policy. Let's try it again with LIFO. 3, 5, hit, 9. So far all the same. Along comes the 1. It's a miss. LIFO says the last thing put in the cache is the first to come out. In this case, that means the 9. LIFO feels weird to me, and I'll show you why. Here's the 4. Still a miss. What gets replaced? Well, the last thing, which was the 1. That was the last thing I put in. So it gets replaced. The concept of last in, first out is common in queuing theory, which is related to this idea, but I've never seen it implemented as a caching mechanism. A LIFO cache will fill up with the first few items, then constantly replace the last one. It's really cheap to implement. Just use the last spot in the cache once it is full. But you're probably not going to have a good balance locality-wise with this choice. Let's try something else. All right, this is the one you came to see, LRU, least recently used. A little bit of deja vu. So far, so good. And now, a choice that needs to be made. Here comes the 1. That's still a miss. You can draw a line from the 1 back to the list of things inserted until you are 3 items deep. This is the LRU item, the least recently used. In this case, that's the 5. The power here is that the hit of the 3 block increases its locality, meaning it gets kept in this case. Let's do another one. Here comes the 4, still a miss. Draw the line. And now it's the 3's time. Don't cry for it, it had a good run. Because you have to track what was used least recently, the algorithm to implement this policy is more complicated than FIFO. There is a memory cost and a slight access cost to this. The access cost is negligible in comparison to what you're caching, or it should be, otherwise you shouldn't bother caching. But that memory thing might be expensive. You'll see more about how this is done in code in a future lesson. I hear you might want some Python in your Python course. Next up, I'll show you the LRU cache decorator and how to use it. In the previous lesson, I showed you how different caching policies work. In this lesson, I'll introduce you to the LRU cache decorator found in the functools module. Your hardware and your operating system implement caches to help make your computing experience snappy, or at least snappier than it would be without a cache. To take advantage of the same concepts in your Python code, you can use the provided LRU cache decorator. As it is a decorator, it is used by wrapping a function that you already have. You might use it if your function does a lot of computation, or if your function does an operation that is slow, like accessing the network to fetch a document. I'm going to stick with the first case as it means writing less code to demonstrate, but in any situation where the results take time and might be reused, that's a situation where you might consider caching. Now for a quick aside. Spoiler alert, there's a long aside coming later. Understanding a bit about computation may help you better understand when a cache may be useful. Big O notation represents a bounded runtime for a computation. The O is short for Ordnung, which means the order of approximation. My apologies to any German speakers in the audience for butchering that pronunciation. All orders are relative to the amount of data given as an input. Order 1, also known as constant time, means that no matter how much data is involved, the amount of time it takes is the same. Getting the first item from a list is usually order 1. The length of that list is irrelevant to the cost of accessing the first item. Linear time, or order n, is a runtime that is proportionate to the amount of data. Finding the largest value in an unordered list is order n. You have to scan the whole list. Quadratic time is where things start to get messy. In this case, the runtime grows with the square of the amount of data. And on the higher end, you have exponential time, where the runtime grows with the exponent of the amount of input. This last case is a really good one for caching. It gets expensive really fast. The example I'm going to be playing with is the Fibonacci sequence. This goes from costing microseconds to calculate early on in the sequence to 7 orders of magnitude slower than that by the 35th spot in the list. Exponential can bite you quickly. In case you're not familiar, let me briefly introduce you to the Fibonacci sequence. Although it sounds like it might be yummy smothered in an Alfredo sauce, the Fibonacci sequence is a numeric computation named after an Italian mathematician who documented the concept in 1202. As with a lot of things in history, it was discovered long before that, but the first European to write it down gets the credit. The sequence goes like this. You start with a 1, then another 1, then you sum those two values to get 2. And I didn't even have to use my fingers. The next item in the sequence is the sum of the previous 2 numbers. That would be 3. So then 5, then 8, and it goes on forever. Interestingly, this kind of geometric progression is common in nature and is related to spirals. The number of seeds in each ring of a sunflower follows this kind of sequence. This algorithm is best tackled with recursion. Let's go take a look. In the top window here, I have a program that prints out 10 digits from the Fibonacci sequence ending with the number passed in on the command line. Lines 3 through 7 are the recursive algorithm. If the number in the sequence is 0 or 1, then it returns 1. If the number is more than that, it is based on the 2 previous numbers in the sequence summed together, which here I'm using recursion to calculate. Lines 10 through 12 get the command line argument and turn it into an integer, then calculate the range of numbers being requested. I'm using 0 to indicate the first number in the sequence because I'm a programmer and lists start with the 0th item. Lines 14 through 16 loop through the range, printing each of the numbers. Alright, let's try this sucker out, starting with the first 10 digits. That was quick. Let me scroll back here. And there's the familiar 1, 1, 2, 3, 5, etc. Let me try that again, ending with the 15th in the sequence. Still quick. It won't get messy until you get higher up. With me so far? Okay, with that established, I can talk caching now. Python's implementation of the LRU cache is provided as a decorator inside of the functools library. All you have to do is wrap your function with the decorator, and you're instantly cached. That's it, it's that easy. Let's go play with it. To understand performance improvement, you need to measure performance. Here, I've modified the previous code just a bit to add some timing information. The Fibonacci function is the same, but inside of the for loop at the bottom, I'm printing out both the result and how long it took to get the result. I'm measuring the time by calling the time module's perf counter function and finding the difference between the value from before and after the call. Let's see this in action. You've seen the first 10 digits before. Note that although it is pretty quick, there's 2 orders of magnitude difference between the first digit and the 11th. Let's do it again. By the time you get to the 31st digit in the sequence, you've got a difference of over 300,000 times. Let's take this up a few more digits. And by going up just the 5 more digits, you are now into a place where it is easily discernible by humans. This is the cost of an exponential algorithm. So, let's cache this sucker, yeah? Same basic code, just a couple of new additions. I import the LRU cache decorator from functools. I wrap the Fibonacci function with that decorator. And finally, I've added a little bit of debug through a print statement in the Fibonacci calculation. Before I do this, take a guess. How much difference do you expect? Well, here it comes. Pretty awesome, right? You've got the 35th number coming out at a speed similar to the first couple of numbers. To understand how this worked, think about the print statement that I added. It's the first thing that gets run when the function is called. As the calculation is recursive, calculating the 35th number should end up calling the function 36 times. But the print statement is only showing up once between the 34th and 35th. That is because of the cache. The decorator gets called before the function does, sees that it has a relevant value, and returns that value instead of calling the function. As each call to the Fibonacci function uses the 2 values before, you're guaranteed to have them in the cache, which means once the cache is primed, you only need to do 1 computation per number. Let me scroll back here and you'll see the cache getting primed. The first time through, for the 25th number, the function gets called for each number before it. Calculating the 25th number took 0.000131 seconds. But the 26th number had a primed cache. All the values that preceded it were in the cache, and so this number gets calculated 2 orders of magnitude faster. What's more, each subsequent calculation takes a similar amount of time. That's the power of a cache. There is a small but in all of this, which is due to how the decorator is written. To achieve this speed, the cache is implemented using a dictionary. The keys in the dictionary are the arguments to the function being wrapped. That means you can only use the LRU decorator on functions whose arguments are hashable. If your function has an argument that can't be used as a key in a dictionary, your function won't work with the LRU decorator. Another minor thing, due to how the arguments are inserted into the dictionary, the LRU decorator considers the order of arguments important. If you're using two named arguments but passing them in a different order in a future call, you'll get a cache miss. So foo called with a equals 3 and b equals 4, and foo called with b equals 4 and a equals 3, although programmatically the same thing, end up taking two distinct spots in the cache. These restrictions aren't too bad. As long as you can live with them, you can get the power of caching with an import and a single line of code. The LRU decorator takes some optional arguments. In the next lesson, I'll show you how to use them.